Hey gang! So, welcome back to another thermodynamics video. In today's video, we're going to define a few different property terms. We're going to talk about what the Gibbs phase rule is, we're going to derive and define enthalpy, and we're going to talk about a few different types of heat capacity. So let's get into it for today. So we've talked about in thermodynamics why thermodynamics is so important. It's heavily related to energy generation. We've talked about its relationship with transportation and also when you're dealing with chemical separations. Thermodynamics talks about the physical limitations of what's possible and impossible on from an energy standpoint. And this is why it's really important to have a good understanding of thermodynamics so that you can design things accordingly. Now, in thermodynamics, there are a few different property terms that we want to be aware of to help us when we're doing our calculations. In particular, we've got two new ones for today, which are a state property, which describes the condition of a material or system at a particular time. It's independent of how the system or material reaches that condition. So irrespective of how we get there, all that matters is where we are. Conversely, there's also something called a path-dependent property that describes the path for how a material or system reached a particular state, and it is dependent on how the system or material reached that condition. Now, a couple of other terms that we have for today are an intensive and extensive property, where an intensive property of a system is independent on the size or amount of the material in the system. So a few examples of that are temperature, pressure, specific internal energy, density, and specific volume, which specific volume is the inverse of density. So it's got units of volume per mass, but you can also have specific molar volume, which is volume per moles. Now, an extensive property, you would probably guess, is the opposite of an intensive property, and you'd be correct. So an extensive property is dependent on the size or amount of the material in the system. So in this kind of situation, some examples would be mass, volume, internal energy, and work, right? And internal energy in this case is not on a per mass or per mole basis. So it is actually dependent on how much material we had in the system. Now, I'd like to put in context some of these different properties and go work through a little example with these. So I'm going back to our energy generation example where we've got the boiler, steam turbine, condenser, and pump. However, in this situation, let's just simplify. We've got energy coming in. I forgot to mention that. And now in this scenario, let's focus in just on the boiler. So with the boiler, we've got liquid coming into the boiler. We've got the boiler and heat coming in, and then afterwards we've got a vapor coming out. So looking at it, we've got liquid coming in, we've got some properties with our liquid. We know that the pressure is 2 bar, it's 120 degrees Celsius for the temperature, and we have a specific internal energy for the liquid, and we're going to say that this is a saturated liquid. So we put a little bit more energy in, and our liquid is going to start vaporizing. Now, if we think about this, pressure, temperature, and specific internal energy, none of those require us to know the mass or any other property of our system. These are all independent of anything else, and therefore these are all intensive properties for my system. And I also want to point out that the specific internal energy is a state property. It doesn't matter how we got to the pressure and temperature we're at. All that matters is we're at a pressure and temperature of 2 bar and 120 degrees Celsius, and we know what our specific internal energy is. Now, we talked about that we're going to have heat going into our boiler, and then afterwards, we've vaporized our liquid, and now we've got a steam that's exiting, where the steam is at 2 bar, 400 degrees Celsius, and we have a specific internal energy of 2,967.1 kilojoules per kilogram. And once again, pressure, temperature, specific internal energy are all intensive properties, and that specific internal energy is a state property. Now, the next question you probably have is, well, how much heat did I add to my system? And that's a good question. And in order for us to solve this, what we're going to do is we're going to assume all that heat coming in is getting converted into internal energy. Now, I do need to give a disclaimer. This is not the right mindset and the right energy term we should be using. And the reason why is because we have an open system. But we haven't talked about that yet. We're going to talk about that a little later in the video. So for the time being, let's just work with internal energy. It'll be sufficient. So we know for this situation, we're going to assume all the Q coming in is going to become internal energy. So what we can say is that Q, and I'm going to use Q dot to indicate that we are on a per time basis, because this is an open system, is going to equal our mass flow rate, so this is the mass that's moving through our system, times the change in specific internal energy. Now, in this case, we are going to need a mass, which is an extensive property, and that's going to allow us to then calculate our heat, which is another extensive property because it's dependent on how much mass and material we have in our system. So if we pretend that we have a mass of 1 kilogram per hour, we now can calculate our heat. We multiply it by the change in specific internal energy, and now you get that your heat coming in is 2,462.6 kilojoules per hour. Now, if we revisit this again, we change the mass, we make it 10 kilograms per hour, you would know and see that your heat requirements are going to change. They're now going to become 2,626 kilojoules per hour. And so this is one illustration of why heat is an extensive property. It's dependent on the mass in our system. So now we've talked about these intensive, extensive, state, and path-dependent properties. And I'll add in, since we're talking about path-dependent, that heat is path-dependent. It's going to depend on how did we get to that final state. The path matters. Now that we talked about those, there's another handy rule that can be used to relate some of these intensive properties to define a system. And that's the Gibbs Phase Rule. So the Gibbs Phase Rule can tell us how many intensive properties we're going to need to know to then set the stage and define our system. And so for this situation, here's our equation. We've got F equals C minus pi plus 2, where F is the degrees of freedom, so it's the number of intensive properties to define the system. C is the number of components, and pi is the number of distinct phases in the system. And one example of the Gibbs, using these properties to define and set the stage for our system, can be like the triple point, where in the last video we talked about using the phase diagram to navigate and identify different parts in our system and the phases. And in the triple point, it's a very special point. It's the only point where you have solid, liquid, and vapor in equilibrium with each other. And that means that there's a very specific pressure and temperature for that to occur. In other scenarios, you won't be as specific, and therefore you have more degrees of freedom, and therefore you need to know other properties in order to set the stage and know everything else of your system. And that's why the Gibbs Phase Rule is really helpful and important. And what I want to do is go through a couple of examples where we apply the Gibbs Phase Rule. So let's start off with water. It's just pure water, and in that case we have one component, one phase. So if we use the Gibbs Phase Rule, we can substitute in our values, and we see that we have 2 degrees of freedom. So that means I need to know 2 intensive properties to then know the rest of the properties for my water. Now, let's say we, instead of just having water, we now add some ice into the system. We say it's in equilibrium. In this situation, we still have one component, but now we have 2 phases. And when we substitute everything in, we'll see that my degrees of freedom are now 1. Because I'm a little bit more constrained, I now need to have ice and water together. And now moving forward, let's say instead of just having one individual component, we now have 2. So we've got our water still. We're going to now add in another component. Let's say it's ethanol. And in this scenario, we have 2 components. We've got 1 phase. And now that leads us to have 3 degrees of freedom. So I need to know 3 different properties of my system. Normally, when you have mixtures, one of those properties is going to be knowing the composition of your system, and that helps alleviate your degrees of freedom. And from there, you'll do something similar to if you had a pure component. Now, if you, in this scenario, let's say we take it one step further, and now we've got two different phases. We've got liquid, and we'll say we have ethanol in the liquid phase, and then we have ethanol and water in the vapor phase. In this case, we've got two components, we've got two phases, and now for our degrees of freedom, we have two. So there's a lot of different combinations and scenarios that we can have, and that's really useful for us in the long run using the Gibbs Phase Rule, because that helps us identify how many different properties we really need to know to fix the state, define our system. Now, I do want to take this moment to also tell you that when we deal with pure components, that's all information that is related to Thermodynamics 1. When you start delving into mixtures, that's where we go into Thermodynamics 2 content. And there's a whole lot to go through when it gets to Thermo 2 with all these mixture interactions, but that's for a later day. So we've got the Gibbs Phase Rule, and there's another property and value that is good to know when you're dealing with equilibrium, in particular for liquid and vapor, and that's quality. So what quality deals with is when you are have saturated liquid and vapor, and you are transitioning between the two phases, the quality is going to talk about the mass, the fraction of mass that is in the vapor phase. And if you have a quality, you can use that to calculate some of the different intensive properties. And this is only useful if you have both saturated liquid and vapor in your system. And if you do, then we can use that to calculate these different intensive properties, where M is our intensive property, such as density, specific volume, or specific internal energy. And it's going to equal 1 minus the quality times the intensive property for the saturated liquid plus the quality times the intensive property for the saturated vapor. Now, we don't need to use this all the time, but it's something to be aware of when you deal with saturated liquid and vapor mixtures. All right. And so now what I want to do is I want to revisit a topic that we just talked about, where I mentioned in that boiler example that internal energy isn't the right term we should be using. And so I want to address that right now. Now, in our pipe, we've got liquid that's flowing in, we've got liquid flowing out, right? That reflects what was happening in the boiler scenario. And if we look at a segment of our pipe early near the entrance, what ends up happening is that we have liquid that's coming in. So it's applying a force on the liquid near the entrance of the pipe. It applies a force. It's now going to push that little segment of liquid forward. And now the liquid that's moved forward is going to apply a force on the liquid that's ahead of it. And that liquid that's ahead is now going to be pushed forward. And as the liquid's pushed forward, it's going to apply a force on a liquid that's a little further ahead. And this process continues throughout the entire pipe until the liquid exits. Now, if we think about that, we've got force and we're applying it over a particular distance. And if we remember when we were talking about our different energy terms, that sounds a lot like work, which it is, because work is equal to force times length. Now, because we're dealing with a pipe, there's pressure in the system, and we can now use pressure and force, relate those two together. We can say pressure is equal to force over area. We can rearrange so that force is equal to pressure times area. And now we can substitute that into our work equation, where it's pressure times area times length. And from here, we can take that area times length, and we can set that equal to volume. And now we'll simplify our work equation a little bit more and say that work is equal to pressure times volume. Now, because we have an open system, I do need to refine my work equation just a little bit to reflect the open system. And that means that I'm going to need to put dots on top of my work and my volume to reflect that things are in motion, we have an open system. Now, with this system, what I want to think about And I forgot to mention that we can also redefine work and say that it's mass flow rate times pressure times specific volume. Because if you look at mass times volume, the units will cancel out, giving me a volumetric flow rate. Okay, so now if we revisit and we look at the pipe, we've got these different segments that are moving forward. If we look at the inlet, we have fluid that has work done on it by the fluid behind it. So there's work being done on the fluid right at the entrance. And that means that we have work coming in. That's P in times V dot in. And as we get to the exit of my pipe, we now have fluid performing work on the surrounding system. And that becomes work out equals P out V out. And when we combine those terms together, that's going to be my flow work. That's the sum of the work that is being performed on my fluid, both the work coming in and work coming out. And we can rewrite my flow work as P in V dot in minus P out V dot out. Now, what I want to do is I want to take this equation, I want to rearrange it just a little bit. So we've got our flow work equation. If we now think about, because P in V in minus P out V out sounds like a delta term, we can write that as delta P times V dot, and that equals P out V dot out minus P in V dot in, right? Final minus initial. We could then also, perhaps since we want to rearrange that P out V dot out minus P in V dot in, we can rearrange that. We can just multiply both sides by -1. And so negative delta P V dot is equal to P in V dot in minus P out V dot out. And now what we've done is we can now say that flow work is equal to negative delta P times V dot. And from here, what we're going to do is we're going to look at an energy balance, which we haven't spoken much about yet, but we will later. If we look at the energy balance, what we're going to do is think about, we've got our accumulation energy terms, which is a combination of internal energy, kinetic, and potential energy. We also have our transitory energy terms, so that's heat and work, and that's both shaft work and flow work. So those are the energy terms that are in motion, that are either going into or out of my system. And when we have this, what we're going to do is we can take that flow work term, we can now put in that negative delta P V dot term. And if we move that delta P V dot term over to the left side, you now have delta U plus delta P V dot plus our kinetic and potential energy is equal to heat plus shaft work. Now that change in internal energy plus your flow work term, those two can actually get combined together. And that combination is the new term. It is an enthalpy term. So it's the combination of internal energy and flow work. And that is our term that we would be using when we have an open system, because open system is going to always have flow work. And enthalpy, just like specific enthalpy, like specific internal energy, is a state property. So we define enthalpy as U, internal energy, plus PV, and we can have specific enthalpy and molar enthalpy. Same way to calculate it, either U hat plus PV hat, or U underbar plus PV underbar. So that enthalpy term is the other term that we want to, the other energy term, and the one we want to use when we have an open system. And so now that we have that, there's one final term that I want to talk about in this video, which is heat capacity. So heat capacity, as you probably have heard from your high school chemistry classes, is the amount of energy necessary to increase the temperature of a unit of material by 1 degree, right? I'm leaving it very vague because you can use different units of mass, you can use different units of temperature. So heat capacity is a little bit more flexible with this definition. So in this scenario, we can have a box, we can have a material inside. Let's say that we've got helium, and we have a mass of helium of 150 grams. We have an initial temperature of 50 C. We have a heat source in our system. We add some heat. In this case, we'll add 450 joules. And we're going to measure the final temperature, which we found is 50.97 degrees Celsius. My heat capacity is going to be calculated by taking that heat going in, and we're going to divide it by the mass times the change in temperature. When we substitute in our values, we end up getting a heat capacity of 3.09 joules per gram times degrees Celsius. However, what if we didn't have a rigid container? What if we decided to make it a little movable, kind of like a piston? So if we do this, so let's now say we've got a similar container, similar dimensions, just one of our sides can move around, and a piston. We've got same exact mass, we've got same starting temperature, we've got the same heat coming in. We measure the final temperature and we notice that now the temperature goes to 50.58 degrees Celsius. Okay, there's a different final temperature. All right, we're going to think about that in a little bit. So let's go back and let's keep calculating our heat capacity. So it's, again, our heat going in divided by mass times change in temperature. So we substitute everything in, and we get a final heat capacity of 5.17 joules per gram times degrees Celsius. But wait, we just calculated before with the rigid container, and it was 3.09 joules per gram times degrees Celsius. Which one's right? Something doesn't make sense. We've got two different heat capacities. They both can't be right, can they? Well, that's the whole thing with this heat capacity, is that there's actually two forms of heat capacity. There's a constant volume heat capacity, so that's when we use the rigid container, and that one is speaking in terms of like changes in internal energy with respect to temperature with a fixed volume, compared to a constant pressure heat capacity, which is going to speak in terms of changes, the change in enthalpy with respect to temperature at a constant pressure. Now, these are both correct because you can have both types of containers for this heat capacity measurement. And so that's a really important thing to be aware of and make sure you're mindful of when you're talking about heat capacity, because there's two different types. And both have their merits and are useful in different contexts. So now that's going to wrap up our video. And just to sum up everything, we talked about a state property, which is independent, and a path-dependent property, which is dependent on the path. We talked about Gibbs Phase Rule, that's going to relate a lot of intensive properties to fix and define our state. We talked about quality and how we can use quality to calculate different intensive properties when you are hovering between saturated liquid and saturated vapor. We talked about flow work and a new energy term that comes from it, which is enthalpy. And finally, we talked about that with heat capacity, there are actually two forms of heat capacity, a constant volume and constant pressure heat capacity. So that's everything for this video. Thanks a lot for tuning in, and I'll see you in the next one.